It's another Wednesday, and looks like we continue with chapter that deals with probabilities. In fact, today's plan is to look at the last portion, good morning, of this chapter. So I will be skipping 3.6 and moving to 3.7. The reason I skipped 3.6 is because it teaches you how to actually produce experiments on your own by usually going out the street and start asking people all kinds of questions, and that may not be very safe nowadays. So they say you don't want to do that. You want to skip. So there is a section 3.7 here that introduces with some interesting pieces of the story with this exclamation marks. It doesn't mean that you need to scream out loud, but it just means that you need to multiply the numbers from the one given to the end. So setting here. So for example, if they want you to find 3 with a factorial, that's how they call it, sign, what you do is start with 3 and then multiply it by 1 less, by 2 and then by 1. Interesting, right? So that's what we can practice today on multiplying things. And at the end of this section, they actually ask you to find a few factorials, like here in the exercises, like say problem number 1, they have 6 factorial, and you can multiply the number 6 times 5 times 4 times 3 times 2 times 1, or you could use a calculator. And that's what I wanted to show you today. So I wanted to actually use a scientific calculator. Remember, start typing scientific figures. So the first choice is Decimus, that has ability for us to get that factorial. So that exercise was asking you to find 6 factorial, then to get that exclamation mark, you go to functions. See, there is another menu, main menu, and there's a function menu. And you can see that factorial is here. So you just click on it and you get 720. Or you probably by this time already multiplied the numbers, but that will usually take a while if you get bigger numbers to find this factorial. Let's say if you take 10 factorial, so if I get functions and then factorial, it's already 3 million, more than 3 million. Factorials increase very fast. Turns out you can try to find some, like 100 factorial, for example. Get 100. And then functions, and then exclamation. And we can say, what kind of number is this? Well, it turns out it's bigger than Google. Did you know that Google was also a number with 100 zeros attached to it? Anyways, when you multiply by 10 to the power of 157, you need to move your decimal 157 places to the right. So if you move 2, 4, 6, 8 places, so there'll be 149 extra moves, and each empty spot you will have to fill with a 0. So that'd be 149 zeros at the end of 4, and that's going to be a huge number, and we don't even have a name for it. And that's just 100. What if I put 1,000? What if I just put 1,000, so extra 0? And it says undefined. So there is a number, but it's so big that they cannot even produce it, the calculator. So you just saw a limitation of technology of a scientific calculator. Of course, there's huge numbers that usually we don't work with. Maybe some people like, say, Bill Gates or who knows, needs those big numbers, and those are ones that they design a special kind of editors, so they have a special extension to the calculator that enables to deal with huge numbers. You need to pay for it, but what for? We never actually hear about finding 1,000 factorial, turns out. So it's huge, just very, very big. So anyways, the idea is that we can use calculator to do things up to some extent. And of course, nobody's going to ask you to deal with so big numbers. And here we have exercises like problem 2 that deals with just 15 factorial. So just use calculator and do that. Now, besides factorial, in exercise 3, they ask to find so-called permutations. So let me find these permutations for first. So exercise number 3 that deals with the permutations to choose from 25 to. I'm doing this a little differently, not 25 then p then 2, but 25 comma 2, because if I go back to the same calculator, to the scientific calculator, so go back to main menu, 25, and then functions, right? There is a last row of functions where we saw that factorial. You can see there is a sine, cosine. If you ever heard of trigonometry, you probably encountered this. There is also e and number pi. Pi is favorite, and e is like 2.7. That's another irrational number. So I want to use permutations. So for first they want permutations. And then in the parentheses, you go back to main with 25, choose 2. And this gives us exactly 600. So this is so-called permutations. You say, okay, Alex, what does this mean? Well, if you have 25 numbers, then you can try to select 2 of them. And number of permutations tells you exactly how many ways you can select the 2 different numbers. So on the first selection, you can choose any of these 25 choices. And then when you selected one of them, then 24 numbers left. So then you're going to multiply it by 24 possibilities that you can select the second number. And notice this is exactly going to be the same 600. So if I multiply 25 by 24, it will be exactly 600. So number of permutations shows you how many selections you have to choose from, in this case, 25 to numbers. And similarly, for all of the other possibilities, so we can try another exercise here. Let's say exercise number 8. It says find permutations from 52 to choose 5. Okay, permutations 52, comma 5. So that's how I can put this in a calculator. And definitely this is the fastest possible way, because when you just use technology, that's definitely helpful. So I can do it two ways. I can first put this in the calculator. So 25, go back to main, right? And then 52, choose 5. And then I will do it by hand. I say that's 311 million. Yeah, that's a big number. So all these factorials and their cronies, such as permutations, they a little bit too long to calculate. But choose 5 is good. We can do that. So 52 choices for the first position. Then for the second position, I will have one less choice, 51. For the next is 50, exactly 50. That's the third one. See, I keep going down by one. When I say just like in factorial, yes, but we stop at fifth factor at 48. So this way, I have my permutations. And of course, I can here again. So it's 52 times 51 times 50. So just multiply numbers that start at 52 and go down. And please notice that's exact same thing as if I used my permutations formula that is used by the calculator. So I don't want to use the formula, just try to do this with calculator, and this is faster. So 5, selecting 5, well, very possible to do. But if they ask you to select 50, well, you'll need to multiply 50 numbers down, and that's definitely not something that you want to proceed with. But if you put this in the calculator, it will take you no time. Just the time taken me to enter 52,5, because calculator doesn't care. The number is going to be, I think, pretty big though, but it doesn't really matter, because for a calculator takes same as long as to calculate small numbers as to calculate big numbers, right? So I guess that's the point of story. That's why I highly recommend you to use a calculator, and the one that I just showed you, Scientific Desmos calculator, will be, I think, very useful. So I will keep on using it. So eventually, I'm sure you will decide to try also, unless you have your own calculator that you know how to use, and that will be the best thing to utilize. So this is all used in the various little exercises. So let me try to do problem number 19. I think that's a good example of permutations. Number 19 that says the company flies to cities A, B, and C, Austin, Boise, and Chicago. So if you look at the various routes that could be produced, then you could mark it as route A, B, C, where you start at Austin and then end up at Chicago. So start at A, right? So the question is, how many other routes are possible? So how many other routes? Well, you could definitely try to see if you start to permute these letters, like if I keep A in the first position, but then go to Chicago and then Boise. So if I go ACB, that'd be another possibility. Or I could put on the first position B and then have AC, or switch this two around and get C. So those are two more with B on the first place. And finally, I can start at C, right? And then AB, and again switch these two and get BA. So it looks like 6 possibilities are listed, and that's nice and intuitive, but you could have said just from my 3 possible routes, you want to do permutations on all 3 of them. So 3 comma 3, which is going to be nothing but 3 factorial, or on the first place, I have 3 selections, just as you can see here, 3 groups. One was A in the first place, the other was B, and the third was C, right? And then in the second position, I have a choice of 2 letters, because I can put either B or C or switch them around. And finally, for the last place, I can only use 3. So looks like this is going to be 6 for the answer. And of course, if you want to do it the third way, this exercise, and probably some people would say I'd rather just use a calculator, just put 3 and then factorial and get my 6. Or when you say, Alex, you never actually did permutations, so okay, the other way would be to use permutations. See, it's a nice exercise because it has various ways to be approached, because the answer is always the same, right? No matter how you solve the problem, the answer has to be the same, cannot be different. So either permutations or factorial, or actually produce an entire sample, right? In statistics, we call it as a sample. So all possibilities shown here. And that's a third way of doing the problem. Of course, you don't need to do the same thing 3 times. It's kind of a waste of time, right? But it's good to realize that nice exercises are it's possible to be done whatever way you approach. Because if problem is difficult, it means you started one way, you can't do it, so you have to start it over again and try it the other way. And if you can't do it the other way, well, you think for more and more time and try it third way, and eventually you will be able to get to the answer. And that's what makes problems, people say, challenging, until you find that only way to solve it. Well, you're going to be stuck probably, right? So worth to think about. But the point of story, this is a typical permutation exercise. So you choose 3 cities and you start to permute. Permute means switch their positions around, and that each permutation produces different route.
And Professor, do we do the same way for the other part of the questions that it says a total of 8
Oh,
cities?
thank you. Thank you. I forgot there is another part of the exercise. You're absolutely right. There is a second part of the problem that is not the same as this first, but you're absolutely correct. So second part, if you have 8 cities and they want you to fly all of them, right? All 8 cities. So you choose all 8 out of 8. So it looks like, yeah, you can go permutations from 8, choose all 8. Very good. If you're paying attention, that's very good and impressive. So let me also try to do that. So I guess I'll just use the formula. I'll just go for permutations. So click on functions, right? Permutations. See, that's a new word, permutations. I think that's something that one needs to get used to little by little. And the permutations are very big number of possibilities. So please notice 40,000 plus, right? Number of routes between 8 cities. But when they include all of them, 8. Let's say if I want to include 7 or 6, well, there'll be more and more. We're not doing it here, but that makes things longer if you just add more and more, and that's definitely something that will be considered as a little bit more challenging exercise. So when I return back to this nice textbook, I will see there's something else here besides permutations, but I think it'd be probably a little bit too much to load you with combinations. That's something maybe I'll leave for the next time, because I don't think it's a good idea to mix them, because turns out the permutations, combinations is something that we are going to use, of course, till the end of this semester, but it's not as straightforward as people sometimes don't like it. So it takes a little time to get used to it. So I think over weekend it'd be good if you just look at the permutation part of the section. I'll do one more exercise that will just show you an idea of permutations and combinations. I think exercise 22 will be a good example. And then maybe I'll stop at that stage. I think I don't want to overload you. Definitely it'd be an overload with this thing. So I'll do 22. So part A is, again, you start to choose committee, different committee members. It looks like there are 4 selections. So what they want you to do is to choose out of 12, total is 12, 4 people only. So when I do that, I'll use permutations from 12, choose 4. So that's part A of the exercise, analogous to everything we've done so far. So I can, again, use my favorite calculator, very proud it is available. So functions, permutations, right, and main to enter 12, comma 4. So lots of possibilities. So if you want to select 4-member committee out of 12 members, there be 4 positions, and I have 12 choices to elect. Let's see, who do they elect? Let me see, go back to this textbook. So they want to have a chairperson. Okay, so they elect chairperson. 12 people could be chairs, any of them. Then vice chair cannot be the same. So now I have 11 selections for the second person, because once I already selected the chair, then it cannot be the same as a vice chair. So I have only 11 people. And turns out and means times, where you saw this, right? Times. 2 people are gone, chair and vice chair. Then there is a second vice chair. So there are 10 choices for that position. And finally, 9 positions for the secretary. So I hope this is something that's kind of clear, but it is still worth to think about this. So I can just double check. So if you take 12 times 11 times 10 and then times 9, right? So we have same 11,880. And that's our first part. So we basically select 4 people, but then we start to permute those people. What does that mean? Well, I select a group of 4, and then it makes difference if you're a chair or if you're a secretary, right? So there's some ways of permuting them. In fact, it turns out that there are 4 positions that you can put a person from committee that you already selected. So you're selecting 4 people, but then any one of them could be a chair, and 3 remain for vice chair, and then 2 more remain for second vice chair, and then only 1 for secretary. So one can say it's like 4 factorial possibilities to switch these people around, right? To have a chair, and then first vice chair, and then second vice chair, and then the last remaining position will give to secretary. Well, say, Alex, I want to be secretary, so I want to start here. Yeah, you can commute this product, doesn't really matter. Still going to be the same thing. So same result at the end, 4 factorial possibilities. So I'm trying to say a couple of words about part B that says, what if you don't care? What do you mean don't care? What if you don't care who's going to be a chair, who's going to be vice chair, who's going to be a secretary? Doesn't matter at all. So it's just a ethic subcommittee with 4 members. So there's no chair, no vice chair. So all these permutations would not matter. So if you selected 4 people, you can also permute them 4 factorial times. Or if you selected the other 4 people, let's say you selected first 4 from this 12 candidates, or you choose last 4, or any 4 candidates from this group. And if you start to permute them, you get various positions. But if you don't, well, it turns out number of permutations for these 4 is always 4 factorial. So you select a different 4 people is another 4 factorial. It's another 4 factorial. In other words, how many times 4 factorial fits into this total 11,880. So in other words, I will divide if I don't care about ordering those people. So if I take this 880 and divide this by 4 factorial. So if I put division by in the functions again, I need 4 factorial. So I need to put 4 first, right? And then function, then factorial. So nowadays it's 495. 495 possibilities if I don't permute these numbers. And 495 turns out is going to be exactly number of combinations out of 12 to select 4. And of course, I can check this out with a calculator, and that's how the combinations appear. But I meant to do it next time, so I think I will just stop at this stage. Just let me double check. So I go combinations, and then back to this 12 people, and then comma 4, and of course it has to be the same exact thing. So once I select 4 people out of my group, I don't start to switch them around. So each switch is 4 factorial. So you kill all those permutations by dividing by number of ways to switch those people around positions by, in this case, 4 positions. So it's 4 factorial. So it will be actually the result such as a 495. And that's how we'll calculate all of the combinations. Turns out that's all I have to do in here. And that's something that's interesting and deserves some time thinking. So that's why I think that's a little bit maybe getting too much on you. And the rest of the section will deal with this idea of combination. So I want to discuss it next time because it'd be really too much, and I know you might be already feeling that you need a break, right? So let's have a break. Let's have a break because I think you did pretty good. We covered lots of material, and on Monday next week I will finish up with this combination story, and over weekend maybe you can try to do a problem that we utilized today, and of course see if you can use that scientific calculator which is built into that Desmos program, or if you have your own one, because I know that some people have a graphing calculator such as Texas Instruments or Casio, and they also calculate permutations, combinations. Maybe you already took statistics class and saw it, so it's fine with me. You can do it any way you like. But the point is, it's a good idea to try over weekend, right? Because we will be using this so-called combinations from now on. So we'll see them in chapter 4 and then in later chapters of this statistics textbook. So I think it's a good moment to stop, and we will, of course, continue with the same thing next time. And I'm going to stop this recording and see how you feel about the class, because I have very good feeling. I have a feeling that lots of people in this class are doing just perfectly good, and that's the way to go. So you are doing good. That makes me very happy.